Hi, I'm Daniel Woods, a cybersecurity lecturer at the University of Edinburgh in the United Kingdom. Today, I'll be introducing a statistical model that allows us to measure the causal role of cybersecurity, rather than just assuming the answer based on received wisdom. In particular, this model helps us to design experiments by identifying which independent variables need to be included. The causal model also provides a framework to interpret and reason about the many empirical cyber risk studies that you may come across. Before introducing the model, it's useful to first begin with a naive model of security. So, a natural law might go something like, the more security a firm has, the less harm they will suffer. This is almost true by definition, and we can describe this visually here, with the negative slide denoting a negative relationship in which more security leads to less harm. Yet, in the literature, we find results with the opposite relationship. For example, Sen and Borla find that higher security budgets are associated with higher frequency of data breaches. So to illustrate this relationship, we have here artificial data showing the exact same relationship. The line of best fit shows that the entities who invest more in security tend to also suffer more harm. Now, this seems to contradict our natural law. This is because the simplistic and naive model we introduced does not include a confounding variable. It's not the case that security investments cause greater harm. Rather, entities who anticipate more harm will also invest more in security. This is often because these entities face a higher threat level. And we're using this term to capture the motivation, capability, and activity of adversaries. So to illustrate the role of the emitted variable, we divide our artificial data into two threat levels. The red dots face a higher threat level. Let's assume, for example, that these are banks who are juicy targets for cyber criminals, and the blue dots face a lower threat level. These could be neighborhood pizza shops that might not be worth the criminal's effort to target. On average, as we would expect, the banks spend more on security, which is a rational response to facing a higher threat level. Now, if we fit a separate line of best fit for the high threat population, we see the result that we would expect. More security is associated with less harm. This suggests that our statistical model should include variables in addition to security. It shouldn't be this naive, direct relationship between security and harm. This follows because an active threat actor is the only necessary condition for harm to occur. Thus, the cause of harm is the threat actor. Therefore, the backbone of our model should be a positive relationship between the threat level and harm, which can be seen here. However, all hope is not lost. Firms can take actions that reduce expected harm for a given threat level. We use the term security level to describe the aggregate of all these technological controls and processes that we would describe as security. Here we have the expected relationship for a given threat level, namely, a higher security level leads to less harm, all else being equal. In this sense, we say that security moderates the relationship between harm and the threat level. Now, there are also actions a firm may take that typically unintentionally increase expected harm. So examples of this include retaining more personal data about customers or giving more employees administrative credentials. Note, these decisions may be taken without any input from employees with responsibilities for security. So for example, marketing teams may want to retain more personal data. So we use the term exposure level to describe the attack surface and at-risk assets belonging to the firm. Here we have a positive relationship in which more exposure is associated with more expected harm for any non-zero threat level. So, this is a great model in theory, but it faces two practical problems. First, these variables are difficult to measure, and second, harm is relatively infrequent, which complicates research design. So, we now describe how we extend this basic model to address these concerns. So first, the measurement problem. The seductive solution is to enumerate, observe, and aggregate all security controls. Unfortunately, it is in reality impractical to measure all such controls. For example, network scans are a common data collection method used by both academics and practitioners to measure a firm's security. However, scans only provide information about internet-facing infrastructure and provide little information about internal controls, like, say, for example, detection technologies or security reviews during internal app development. So, you might ask, what is the way forward, given we may not even measure the most important controls? We argue that we should instead think of each control as an indicator of an unobserved security level. These controls may have no effect or even a negative effect on the security level, but they still reveal information. More secure organizations typically are more likely to implement controls. So a given control provides probabilistic information about the overall security level, regardless of the causal direction. For example, hiding web server information does not directly mitigate web vulnerabilities. However, it could be the case that firms who hide web server version information are also more likely to conduct rigorous internal code reviews that would reduce the likelihood of web compromise. So, clearly, these relationships are noisy. For example, imagine you only measure, say, a handful of controls. It's possible that an insecure firm implements those controls, but does not implement the controls that you do not measure. Based on the available measurements, this firm would look like it has a high security level, whereas in reality it may not. Now, this creates uncertainty and statistical noise, and broadly speaking, we can overcome this by making multiple measurements and aggregating the results. The more measurements, the better, which is a story borne out in the academic literature. So, in the language of structural equation modeling, the measurement of each control is a reflexive indicator of a latent variable, namely the security level. This provides a pragmatic way of measuring firm-level security without needing to observe every control. It remains an open question whether security level is, say, a general trait that performance across all security tasks, or whether in reality there are multiple latent variables for different kinds of security. For example, patch cadence, employee awareness, or incident response. So this kind of leads us to ask the question, are firms who patch more quickly more likely to have employees who follow security policies? We, the academic community, don't know the answer to this. This is still an open question about whether there is this general security level or whether there's in fact multiple. So, now we move on to the second practical problem, which is that harm occurs infrequently and the harmful event, say a data breach or a ransomware incident, may not be disclosed to external parties. So we might have, for example, a situation in which we observe a compromised web server that's, say, hosting malware, but we may not know the dollar impact on the firm who owns the web server. In this scenario, we could conduct a mitigation study by measuring the relationship between observable security measures and web server compromise. However, we would not be able to establish a statistical link to harm because we don't observe any variables for harm. In other cases, we may have a sample of firms who were compromised. For example, a set of firms who were popped by a ransomware gang who subsequently leaked their data. We would know who the firms were, we would know that they were compromised by a ransomware gang. But in this case, we might be able to study the harm. So for instance, we could look at change in the stock market value of those firms following the incident, and we would call this a harm study. A harm study could, for instance, explore the relationship between this proxy for harm and security controls like full disk encryption. So now we have two types of study. One with compromise as the outcome variable, and the second where compromise is an input variable. Thus, it makes sense to add compromise as an intermediate variable in our model. This essentially splits security into two. There are those controls and processes that impact the likelihood of compromise, and also separately those controls and processes that impact the extent of harm suffered following a compromise. We call these preventative and reactive security, respectively. So, in the same way, we can differentiate between the role of exposure before and after an incident. So surface exposure captures attack vectors used to achieve compromise, such as the number of accounts with administrative privileges, whereas asset exposure relates to factors that amplify harm resulting from a compromise, such as, for instance, the volume of personal data of customers retained by the firm. So this full diagram is our causal model of cyber risk, and you can read more about the model in the paper where you see the reference here. This introduces the model in more detail and classifies the literature based on which of these bubbles are investigated and also the causal relationships between them, and we do that across 78 empirical studies. So that was the end of this unit. The following units will delve deeper into empirical work associated with various bubbles within the causal model. Thank you for listening.